Okay, guys, let's try all to wake up. It might be hard for some people to wake up, but let's try. Okay, so I'll tell a little bit about myself. My name is Konstantin Kladko. I'm the CTO of Scale. Actually, I'm a scientist, so I did lots of physics in my former life. So I was at Los Alamos National Lab in New Mexico. Then I worked at Stanford University, Department of Physics. And then actually what happened, I joined crypto. The way I joined crypto, there was a startup which Professor Bonnet at Stanford started. Maybe some of you know him. So I joined the startup. And then that's actually how I actually moved to crypto. So since this time, I've been to one startup, another startup. It was really interesting. And then we started Scale. And Scale is a network of Ethereum-compatible blockchains. It can run websites, it can stream music, show images, videos. It's really interesting. But today, I'm actually not really going to talk about Scale. I'm going to talk about proof-of-stake consensus and mathematics, which is related to this consensus. So my best desire is when you guys leave, you will know more about consensus than what you know now. Okay. So let's start. Let's start with waking you up a little bit. So please raise your hand. What do you know about blockchain? If you know about how it works, right? So if you just have a vague feeling how blockchain works, please raise your hand. Wow, okay. Then if you know well, please raise your hand. Okay, and if you can build it yourself, please raise your hand. Raise your hand, guys. Anyone can build anything. It depends. Depends on time. Just raise your hands. Anyway, so hopefully after this conversation today, more of you will know more about blockchain. Okay, so that's a very simple definition. Blockchain is a network of computers that accepts transactions from users. Users usually send money, or they try to make money. So these are transactions. They send something to blockchain, and then what blockchain does, it orders them in blocks. So blocks are like deck of cards. You know, like if some of you played poker or any simpler card game, there's a deck of cards and there's an order of cards in the deck. In the same way, on a blockchain, there are blocks, and blocks are ordered. And so what you need to reach consensus on is what's the order of transactions in the block. So you have this deck of cards, but you order them, how they are placed in the deck. That's what is called consensus. Okay, so I have this video. Some of you just can meditate. It's a video of consensus that I made. It's actually our consensus. And I'll just see for a while how it works. So in this video, what happens is that you have 16 computers and they're kind of starting, so it's kind of starting a bootstrapping phase. But once they bootstrap, it's consensus. And you see that on every computer, there are blocks, which are these decks of cards, right? And these blocks, these chains are growing. And what's important is that the blocks look the same on all nodes, on all computers. So this is yellow, this is yellow, this is white, this is white. It's actually a very simple problem. Turns out mathematically, it's really hard to solve this problem. So there's consensus. Just keep on watching for a while. And so you just get a feeling of it. You see that when this is happening, every point here is a network message. So they exchange messaging on the network. Some of the messages are tiny. Some of the messages are really, really large. And in the process, this is the mathematical algorithm. This is the algorithm that runs consensus. And the blocks are being extended and created. So that's consensus. Actually, that was a live one. So before this conference, I made a small tweak in our blockchain. And every time a computer would send a message, it would actually create this point. So actually, what you've seen is actual real consensus. Okay, so let's come back and talk more. So another question to you guys, to wake you up again. Why do you think blockchain consensus is hard to build? Please raise your hand. Answer number one, because internet is unreliable. Raise your hand, okay? Answer number 2, because many computers need to work together. Raise your hand, okay? Answer number 3, because some of the computers can be malicious. Please raise your hand, okay? The truth is actually all of these answers are kind of true, but there's a progression of complexity. Definitely, network is unreliable. Sometimes packets on the internet get lost, so you need to deal with this, right? That's number 1. Number 2, computers need to work together. You have this distributed system, and distributed systems are hard to build, so it's harder. And then the most hardest thing is that some of these guys can be malicious. We assume that some of them can do bad things. And the third thing actually turns out to be really, really hard mathematically to deal with. The second one is also hard. The first one is kind of easy. But these are the problems that we face when we build consensus. Okay, now there are 2 types of consensuses. Proof of work, proof of stake. There are good things and bad things about proof of work, proof of stake. Proof of work, lots of number crunching, you probably know, right? Graphic cards, waste lots of energy. Also know, heats up things. Some people do things like water warmers based on mining, right? Probably secure, you can easily prove security, it's secure. And it's easy to understand, it just requires a high school level of math. You can read Satoshi Nakamoto paper. If you were good at math at high school, you can read it, right, and understand it. And last, it's slow. It takes minutes. Guys, it takes minutes to finalize transactions. Proof of stake. No number crunching, no energy waste, good things. Probably secure. You can prove security for some of them, right? It's drastically much more math. So you replace the number crunching with huge amount of math if you want to do it securely. It takes 10 times more lines of code, more bugs, harder to actually make it right, crashes, more, all kinds of things. It's probably secure, as I said, and requires probably a graduate level of knowledge of mathematics. If you don't have a graduate level of knowledge of mathematics, you can build it, but it won't be secure. And it's fast. As you've seen just here, the finalization time is seconds. Now, what does proving something mean? That's a mathematical definition. Proving is really, really, really a really strong thing. If you prove something mathematically, like 2 by 2 is 4, you can destroy the universe, kill all of the people. 2 by 2 will still be 4. There was a Greek philosopher, Plato. He said that there are 3 types of universes. There's a universe of mathematics, universe of physics, and universe of feelings. And these 3 things are separate. So mathematical world exists independently of physical world. It's a really, really interesting thing. Now, there are several assumptions we are making about blockchain to be able to have it secure. Number 1, the network has to be reasonably reliable. It has to be able to send a packet from point A to point B in a reasonably reliable way. So it doesn't have to be 100% reliable because you can resend things, but it has to be reasonably reliable. And so let me ask you a question. Are the following networks reasonably reliable? First, United States Postal Service. Who thinks that United States Postal Service is a reasonably reliable network? Please raise your hand. Yeah, actually it is. I actually sometimes send tax reports to IRS. And I know it will get lost. So the way actually I fight this, I just send it many times. Just send every day 10 copies, and 1 copy will get actually delivered. Next question is, if you are on a deserted island, have a bottle, you put a message in a bottle, and you wait for people to actually read this message. Is it a reliable network? Yeah, probably not, right? So there's a measure of reliability. It doesn't have to be fully reliable, but it has to be reasonably reliable. And so then another question to you guys. If you think that the computer is malicious, what can this computer do? What actions are malicious? Answer number 1, send false information to other computers. Is this malicious? Yes, right? Answer number 2, attempt to steal cryptographic keys from other guys. Is this malicious? Yes, right? And the last question is, if it just stops doing anything, is this malicious or not? Please raise your hand if you think it's malicious. It It is malicious because it actually can make blockchain stuck. So the bad guys win if bad things happen or if the thing simply stuck. Okay, now let's watch again a different video. Okay.
Sooner than expected, so that life could go on for all of us.
Now this video is a little different because we actually stopped 5 of 16 computers, and you think it works slowly, but at some point it actually starts working again, and consensus still works. So probably secure consensus works even if you stop some of the machines. And the maximum you can stop is 1/3. There are mathematical proofs that show that you cannot have more than 1/3 of bad guys. But in this case, 5 of the guys just stopped them, and so they see the consensus still works. Blocks are being mined, so the algorithms are able to actually take this problem and solve it. If I would stop 6 computers, this thing would stop. They would get stuck, and then if like next day I would actually power on another computer, it would start working again. So that's really important about consensus. 1/3 is kind of a magic number. Okay. Now, really something that you need to know. If you need to remember one thing after this presentation, that's this slide. A blockchain, a probably secure blockchain, is hard to build, but there are phases, and if you make every phase secure, the entire thing is secure, right? If you make a meal and you want it to be fat-free, every ingredient is fat-free, the entire meal is fat-free. Same as here. If every phase is secure, the entire thing is secure. And these phases are incredibly important for every consensus. So what are the phases? First phase is super simple. Okay, so we have a mathematical framework that actually splits things, and our blockchain is one implementation of this framework where, as I said again, if every phase is secure, the entire thing is secure. You can take our source code and change things on every phase, change the mathematical algorithms, and as long as the phases stay secure, the entire thing is going to stay secure. Okay, so let's talk about phases. First phase, super simple. Maybe many of you know it, many of you did it, right? You set a transaction to the blockchain and it just goes somewhere. Usually it goes to something which is called a pending queue on every node. It's really simple. The browser sends it, you know, your mobile app may send it. At this moment there are these pending queues, but pending queues are chaotic, they're not ordered, and you need to order them in blocks. Second phase, super important, is proposal phase. One node, many nodes need to form proposals, and a proposal is a block that wants to be, but there could be many of them. There could be many proposers. So because of this, the next phase is that's where you decide which proposal wins. And you need to have an algorithm that decides. This actual algorithm is called consensus. I'm going to talk about this later. And then there's a always kind of a signature phase. The blocks needs to be signed for historical reasons. If you like next year you want to validate the blockchain, you want to have the signature, so you need to sign the block. And then ultimately there's an interesting phase which is called finalization phase. By this phase, by the previous phase, not all computers may have the block, the winning block. So they need to download this winning block, and to download it, the winning proposal is to be widely distributed. So at this point they download this, attach it to the end of the blockchain, you've seen, and then the entire thing starts again. So these are the phases. Now really, let's watch really fast and try to identify phases. So if you look at how it runs, you see that there are some like tiny messages, big messages. Like these are like tiny, and now I'm gonna have like bigger ones, like these ones, and the bigger ones are proposals, and the tiny ones are consensus messages, networking messages. So this is phases which keep on happening. If you just watch this for a while, you'll kind of see this pattern of phases, the periodicity of it. Okay? So, then blockchain, as you guys now see, is a game. There are bad guys, good guys. Bad guys win if everything is fine, blockchains are mined, and the system is not stuck. bad guys win if the blockchain is stuck or diverges, meaning that it looks differently on different nodes. You've seen just on video that in our case it was looking exactly the same on all nodes. If it diverges, bad guys win. And actually, mathematical proof means you prove that if there are less than 1/3 of bad guys, good guys always win. Okay, the proposal phase, let's talk about this a little more. This is where question is, during the proposal phase, what makes it a bad guy, a malicious guy? If we understand it, we can then later fix this problem. We can address the problem. So what makes it a bad guy, a bad proposer? Bad proposer can do a corrupt proposal, right? Something which doesn't make sense. Then it can propose different proposals to different parties, to different computers, and then the blockchain will diverge. That's really, really bad. Another bad thing that can be done is never propose. You don't propose, you hope that you will get things stuck. And also, you never distribute your proposal widely. So we've seen this finalization phase. If the proposal is not distributed widely, then guys at the finalization phase won't be able to download this. All of these are bad things, and what we need to do mathematically is to fix and address all of them, and then it becomes probably secure. So a magic object is threshold signature in particular. There's a way to do it using threshold signature. There's some other ways, but I'm going to talk about threshold signature way, which is really efficient. So there's a super great mathematical object with signatures, and it turned out they eliminate all of the bad behavior. So how they work? Please raise your hand, guys, if you know what a digital signature is. Ever use digital signature? Okay, let me ask you a very simple question. If you don't have your private key, can you create digital signature? Yes or no? If you think yes, please raise your hand. If you think no, please raise your hand. Right, so you do need to have your private key, because private key actually tells that it's you, and when you create the signature, because only you can create it using a private key, it proves that you actually did this. So then later the government or whatever does a party can come after you. That's the purpose of the signature. Now, threshold signature is a similar thing, but it's for a group. It's where, let's say, we have all of you guys, and you want to sign a statement that you agree on something, like 2/3 of you, the majority agrees on something. So all of you use your private keys, and then it's like a jigsaw puzzle. Your signatures can actually get glued together and create this interesting mathematical object, which is a threshold signature, which proves that a group, not just one person, but a group created this thing. So, question to you, very simple. Which signature you would trust more, threshold or regular? You think the threshold signature is better? Please raise your hand. Right, it's better because it's a group of people, so there's more security. So threshold signatures can be done to eliminate the proposal bad things I just discussed in the following way. When you propose, instead of just proposing, you go to every other computer, every other node, and ask this computer to create this threshold signature, so they all sign the statement that your proposal is good. So instead of just proposing, you create a proposal, go to all other computers, they verify it, and they sign that it's good, and you have this threshold signature, and the threshold signature verifies that the proposal is unique, non-corrupt, you didn't send two to different guys. All of those things are actually eliminated by threshold signature, so you have a safe proposal. Okay, the last thing I want to say about threshold signatures is a really cool mathematical process which is called DKG. We do it in our network. It actually runs on Ethereum mainnet, and it allows you to create keys for this threshold signatures. It turns out these keys are like super magic, and you need to have a specific procedure that does it, and it's called DKG. We open source